I'm about to break some life or death news to the people that are gathered here. Now, I may look or even feel perfectly normal, but I'm actually carrying a potentially lethal disease that has been spreading around this normally quiet, leafy little town. And the locals are gathered here to find out whether I've infected them. And I've got to say, they all look remarkably happy about it. That's probably because it's part of the biggest experiment of its kind. With the help of thousands of volunteers, we are about to simulate the outbreak of a fatal contagion throughout the UK. That might seem like a funny thing to want to do, but if I can succeed, this will save lives when, not if, a real pandemic hits. Our pandemic might be simulated, but global outbreaks of deadly flu are a very real threat. In the last 100 years, lethal strains of flu have swept around the planet 4 times, killing untold millions.
The UK government puts pandemic flu at the top of its risk register. The reason for that is it will happen. There will be another pandemic.
The next virulent outbreak could happen at any time. To predict the devastation it could cause, researchers need to understand how much we move around and how many people we meet. And for that, they need good data. So I joined forces with Ebola doctor Javed Abdulmonam, and we've launched a smartphone app that will reveal how a lethal pandemic virus could strike the UK. Now, the infection started here in Hazelmere.
Pandemic started last night at midnight.
I probably have contaminated quite a few people now.
I think there's a really strong chance that I have got the pandemic.
We will find out how quickly it spreads.
Are some parts of the UK safer than others when it comes to the spread of an infectious disease? Will it reach all parts of the UK? Our BBC pandemic experiment will find out.
And we'll discover how many of us could die.
My word, that's an enormous number.
It is an enormous number. The pandemic that we've started here in Hazelmere might well be simulated, but the information that it gives us will help to answer very real life and death questions. This will be the first ever life-saving pandemic. It seems like there's no shortage of things to worry about at the moment. Global terrorism, the devastating effects of climate change, and volatile world leaders. So I hate to break it to you, but according to the UK government's official list of risks to this country, we actually have another much bigger threat that we also need to worry about. Now, this isn't just a hypothetical disaster. This is something that has happened several times in the past 100 years. Also something that we seem to have forgotten about. Can I ask you one question on camera? Sure. Do you know what was the disaster that killed the most people in the last 100 years?
No, I don't.
Could you have a guess?
Oh no, don't put me on the spot.
That's a question.
No idea.
I don't know.
Oh God, that's a tricky one, isn't it? Is it CO2 emissions?
I would imagine the most recent tsunami.
Tsunami?
Well, yeah, so 2005 tsunami did kill a lot of people, tens of thousands of people. Yeah. Something much bigger, something that killed tens of millions of people.
Probably World War II. First, Second World War. Yeah, the First, Second World War, I think.
War and natural disasters, that's all I can think of.
Generally war.
Yeah, generally war.
Okay, so the actual answer is Spanish flu, which killed up to 100 million people.
Oh, I had no idea.
Just 100 years
Sicknesses.
ago.
Oh, wow.
And killed up to 100 million people.
Oh,
so more than World War I and World War II combined.
That's incredible.
Spanish flu was a truly global contagion, a pandemic. a virus 20 times more deadly than ordinary seasonal flu. It was a new strain of flu that overwhelmed victims' natural immunity. The startling fact is that another unknown and potentially deadly flu virus could emerge at any time, which is why our government needs to be prepared. Dotted around the country are secret depots housing vast stockpiles, all poised for the next big outbreak. Protective kits so that health workers can carry out their job safely, antiviral drugs that can limit symptoms if they're taken early enough. It is critical that the right supplies are in the right place at the right time. But those calculations depend on mathematical models that predict how quickly a virus will spread and how many of us will become infected. Now, with this kind of information, you can make really important decisions. Things like, have you got enough hospital beds? Do you need to close the airports? Have you got enough antivirals? Or how many body bags are you going to need? Now, these are real life or death questions, but you don't get to have a trial run. But with mathematical simulations and computer models, you can try out a few different scenarios so that when the time comes, you can make the right decision and save thousands of lives. To create the models they need, mathematicians use a set of rules, basically a series of equations. These equations predict how a particular disease moves, from person to person, and then from place to place. But to do that, mathematicians need information about us, how we move and who we meet. The more accurate the data, the better the prediction that emerges from the calculations. But how good is the data we already have? Are we as prepared as we can be for the next deadly outbreak? To find out, I'm meeting an expert on mathematical modelling for pandemics, Dr. Adam Kacharski. If you want to build a model of how infectious diseases spread, what do you need to know?
There are a couple of bits of information that are really useful. One is the contacts that people have. For an infection like flu, for example, it depends on who you interact with, who you meet. So that's one kind of data that we really need. The second thing that's important is where those contacts are made. How much do you interact in your community, how much do you travel to other locations, and that can really help us understand how much a disease will spread more broadly outside a single community.
Don't you have all of this data already? I mean, we're in the 21st century, people are being tracked all the time. Don't you already know this stuff?
There is information out there, but it's really not designed for this specific question about how diseases spread. So we might have data about where people are, but no idea of who those people are, how many contacts they're making. On a much smaller scale, there's been surveys of what interactions people have in a given day, but that's not linked to their movements. It's important to link those two things together, to have the movements and the contacts in one data set.
Those surveys, do they cover a big portion of the population?
Generally, because of the effort that's required to survey people, if you imagine writing a diary of all your contacts, it's quite an intensive effort, and the data sets are generally quite small. We're talking maybe a few hundred, 1,000 people.
Wow, okay, so in a population of millions, that's a tiny fraction of the people you might want to capture.
Yeah, we can say something general about the whole country, but we really can't understand how different regions, for example, interact with each other.
And this is the big problem. Pandemic planning relies on limited data sets from the UK, samples of just hundreds or a few thousand people, which means epidemiologists have to make their best assumptions about how we behave. But if the assumptions are wrong, the results could be too, and that could have fatal consequences, unless we can improve the current data. So what can I do to help? What's the ideal situation here? What would you like?
What would be fantastic to have is information on how people move, and ideally not just where they think they move, but actually some way of verifying where they go, and information on who they are, what's their age, what's their professional status, and who they interact with, what kind of contacts do they have, how many people are they meeting, have they met these people before? And if we had all those things together, that would be a really useful data set.
And that would help you work out how a disease might spread in the country?
That could give us a much better understanding of how these things might spread, yeah.
Okay, how many people do you need me to get on board here?
I think if we could get about 10,000 people in this kind of data set, that would be fantastic.
Okay. No problem.
Getting data about the travel and social habits of 10,000 volunteers would clearly be a very dramatic improvement, a step change in the detail available to pandemic researchers. It is a challenge, but the technology that can make it happen is already out there. Smartphones are the perfect tool for pandemic research. Forget the phone bit. It's the combination of a built-in GPS tracker and specially designed apps that make them a data gatherer's dream.
Okay, so here's the plan. Adam and his fellow mathematicians need GPS data and social contact data to be able to predict the spread of a pandemic. And we're going to help him using a smartphone. We have created the BBC Pandemic app, and here's how it works.
Users who download the app instantly catch our harmless virtual pandemic virus. To get the detailed data we need, the app will track their locations anonymously, once an hour for 24 hours. Users will also be asked their age and gender, and the app asks them to record the details of every person they encounter during that 24-hour period. The combined contacts, GPS and age information will be sent to our maths team at Cambridge University. Real data from 10,000 people will fundamentally improve the accuracy and detail of the current assumptions, and so predict with greater confidence than ever before how devastating the next pandemic could be.
This really is the very first time that GPS data has been combined with data about how many people you come into contact with and data about your demographics. And this is an incredibly powerful tool for predicting the spread of pandemics. Now, I don't know about you, but I think that's reason enough to download it. Now, all I need to do is get a few thousand people involved.
This morning, our campaign to get 10,000 app users nationwide begins.
We've built this smartphone app that you can download on all different platforms. It's called the BBC Pandemic.
Our national experiment is underway, but that's not all we're setting out to do. We're recruiting for a second experiment here in Hazelmere in Surrey. We want this small town to give us a close-up view of an outbreak. Watch how a virus spreads from one person to the next.
Take part today and sign up!
If we can spread a virtual contagion through Hazelmere, this unprecedented detail can be used to test the best ways to stop an outbreak. Who should be vaccinated? Should schools be closed? Or places where people gather? We've persuaded nearly 500 people from Hazelmere to take part. They show up as blue dots here on our map. The Hazelmere app is different. Unlike the national experiment, the people here start uninfected and will only become infected if they come into contact with another infected person. This app works by pinpointing their location every 5 minutes for 3 days. The GPS tracks created by each user are sent to our mathematicians in Cambridge. The team will combine all of the tracks to identify the moments when our volunteers overlap. The equations then calculate whether someone becomes infected based on how long they remain close to an infected person. Once the calculations are done, The results will be sent back to the app, informing users whether or not they have been infected, and if so, how many people they went on to infect. The app collects data anonymously, but some users have started filming their daily lives in the moments before the BBC pandemic hits their town. In a real outbreak, any one of them could become a victim.
Hi, my name's Lynette, I'm 61 years old.
My name's Ed, I'm 37, I'm a school teacher here in Hazelmere.
My name is Faye Walton, I'm 41 years old.
My name's Pippa Hollins, I'm a nurse in Hazelmere. I'm just about to have my breakfast with John, my husband. There's John. So good morning, John.
Morning.
My name is Justine Charman. I live and work in Hazelmere.
So it's a nice quiet morning in the apple tree.
Everyone with the app in Hazelmere is susceptible to getting infected. But our outbreak can only start when someone who is already infected comes to town. A patient zero.
The term patient zero is commonly used to describe an individual who first introduces a contagious disease to a community. And sometimes things really are that simple. One person who somehow or other starts everything off. In 2014, when Ebola hit West Africa, epidemiologists tracked patient zero back to a 2-year-old toddler in Guinea. And in 2009, when swine flu hit the UK, it was a plane with 6 infected people travelling back from Mexico that brought it to this country. Eventually, from that handful of cases, 500,000 people would go on to be affected. So, let's imagine something similar to that last flu pandemic. I've just come back from my holiday, and I'm feeling a bit tired, but it's probably just jet lag. And I've got a few errands that I need to run about town. Let the BBC pandemic begin.
I'm now actively infectious, and the app is tracking my every move today. First to the local gym for a spot of yoga. Anyone else with the app is also being tracked. In Cambridge, our maths team enter all the GPS tracks into their model. To create a detailed map that will reveal how the virus actually spreads, we want to infect as many people as possible. So the team has set mathematical rules that mean no one is immune to the virus, and it's highly infectious. Which means I could infect someone up to 20 meters away. But the longer and closer we are to each other, the higher the probability of infection. All I need to do now is to come into contact with as many people as possible. So, time to move on. A spot of shopping, I think. I don't want to attract too much attention to myself today and risk affecting other people's behaviour, so I'm wearing a small camera as I go shopping. Can you recommend me something?
What do you like?
Science.
Well,
Where next?
I work in a shop just over the road from where I live. I've worked there for about 6 years in all now.
You got washers in here?
Yes.
Where are they? So one of them. Okay, gosh.
So today I popped in for a coffee with my friend, and that was really nice.
Thank you very much.
And your food order's been taken, yeah? Thank you.
We're on Hazelmere High Street. We've just left the studio for the day. Everything's all cleared up.
Hello, I'm Mary. This is Mary. This is Mary, okay. And we run the checkouts together.
Right, time for a pint, I think. and my last stop here for the day. Hopefully there'll be a few people in here with the app. But it's going to take a few days to be sure of how far the virtual BBC virus has spread. And all the while, our volunteers are blithely carrying on with their normal routine.
It is the end of the day for me, and it's my favourite part of the day because we're going to go and pick Daisy up.
It's been a really, really long day. It's about 9:30. I've come into contact with loads of kids today. Big assembly, I've taken all of year 7 out.
So it's 11:20, Thursday night. I've just finished work after a very, very long day.
Over the next 72 hours, our maths team in Cambridge will be working on the data day and night, calculating how many of the good people of Hazelmere, or their phones at least, have caught the BBC pandemic from my patient zero walk.
Spanish flu was by far the deadliest pandemic in the last century. At its peak, around 15,000 people died in England and Wales in a single week. It was so virulent, it made people's lungs bleed. Death followed within hours. It was a terrifying variant of the seasonal flu we see each winter. But what makes the radical difference between seasonal and pandemic flu? I'm meeting one of the country's leading experts to find out how a flu virus can transform into a killer that can threaten our nation at any moment.
We think about what one of these viruses looks like to our body. Here it comes. It's basically a bag with all its genetic material in the middle, and on the outside it's got all these little spikes. Now, all these spikes are what's sticking out and being presented to our immune system, and it makes antibodies. The antibodies, we can draw like little Y-shaped things, and they perfectly recognise the exact shape of the spike of this influenza virus, and that's the person is protected against that invading virus.
These antibodies are very specific to that flu virus, so we're immune to flu, surely?
Yes, that would be the case if everything just stayed the same year on year, but it doesn't. And the reason for that is viruses create thousands and millions of copies of themselves in a person as they replicate. Now, in copying themselves, they sometimes make mistakes. So if this virus is replicating and it makes a mistake in the gene that encodes this spike, now the spike looks different. It might be a different shape. I'm going to actually draw it as a different colour here. So now the spikes are all coloured yellow. Okay, it's a bit like you go outside in your coat and then you change it and put on a different coloured coat. You now look different to everybody outside. This virus looks different to all the antibodies that had been induced in the first place to the white virus. So even though you had all those white antibodies, they don't do you any good whatsoever against this yellow virus.
It's this ability of the flu virus to transform itself that can make it so dangerous. When the outer coat of proteins changes in only a small way, that's called antigenic drift. It's still a familiar virus. That's what happens with seasonal flu. These relatively minor changes in the coat of seasonal flu viruses mean our immune system gives us some protection. But the real danger is that a new, completely unrecognizable flu virus will emerge. A virus with pandemic potential, which our bodies have no immunity to fight off and can cause far more damage. Pandemic flu viruses emerge because humans are not the only creatures that get flu.
Pandemics are influenza viruses that come across from other species of animals into humans, usually from birds, wild birds like ducks, geese, swans. And the thing about those viruses is, although they're also still flu viruses, they look just the same on the inside, their coats, their spikes that are on the outside, are completely different.
Because these viruses have got genes from the animal population, it can mean that their coat is dramatically different. That's called antigenic shift. And it can mean the human immune system is entirely unprepared.
Therefore, everybody gets infected. The outbreak is explosive because everybody is susceptible, and we see it ripping around the world in a matter of days and weeks.
Right now, there are several particularly worrying flu viruses circulating in bird populations. So far, those viruses haven't mutated enough to transmit easily between humans. But the fear is they can, which is why we are conducting our experiment. We need as much data as possible before the next pandemic erupts.
All the volunteers in Hazelmere are about to discover their fate. Only the computer model knows which, if any, of the people turning up here are infected. I need to give them a PIN number to reveal their individual results. There's been no dry run. Nothing like this has been attempted before. I'm about to find out if my walk around town had any effect at all. To be honest, it's all a bit nerve-wracking.
To infect you all, there had to first be a patient zero, which you may have guessed was actually me. And we will see if I actually managed to successfully infect any of you. Okay, so if you could get your phones out, I'm going to give 2 different PIN numbers. When you put in that PIN number, it will tell you whether or not you've been infected. If you have been infected, please move over to this side. And if you haven't been infected, move over to that side. Okay, so the 2 PIN numbers are... Drum roll. For Android, please type in 8165. And for Apple, type in 8195. Okay, if you could move to this side if you've been infected, and that side if you have not been infected. Okay, I have to confess, I think we've got a good number of you. We managed to infect a good number of you.
This is a great result. 72 people in this small gathering alone have been infected.
Yes, I was infected. I'm really surprised at the results. I've infected 1 person.
I know exactly where I got infected and what time I got infected, just purely because I'm on annual leave, so I haven't really done much, just potted around the house. So the one time I did go out, I actually got infected.
But this is just a fraction of all our volunteers in Hazelmere. To see how the infection moved from person to person, we need to look at the bigger picture. Our mathematicians from the University of Cambridge, led by Professor Julia Gogg, have finished crunching the data.
The first thing I want to show you is patient zero track, which is you. That's the high street there. So.
The gym there, that's where I go first, and that's where I go to yoga. Here I come.
The blue dot there is one of the users, the other users, and they're uninfected because everyone else starts uninfected. Okay. It's only you that started infected. And let's see what happens when you cross paths with them.
Ooh. And here I come, ready to infect them. So I'm looping around because I'm doing some filming, and so that's them getting infected.
Now they're infected, and they're off up the high street.
So if they cross paths with someone else, there's a chance that other person will get infected.
Exactly, so it's a chance, and the closer they are, the longer they are, infection could happen.
That's 1 person then. That's 1 infection. What happens next?
Well, let's have a look. So So it's looking at zoomed out in the high streets.
This is still me as I'm wandering round, and now there's loads of dots, loads of people who are infected.
So the blue dots are people who haven't been infected yet, and you can see the orange or red with the circle around, and you can see you've got the extra dotted halo around.
And quite, actually, so often I come into contact with people, or people are coming into contact with each other and not getting infected, so it's not every single time.
No, it depends on proximity, length of time.
So that's the whole of Hazelmere's now. So now this is when I went off to the supermarket and in the pub, of course, at the end of the day. Vital way to end the day. We're now at 6 o'clock in the evening. I got there about 10:30 or so. How many people, by this point, are infected overall?
There were 77.
77?
Yes.
Just in one day?
That's right.
From me arriving. Okay. How many people did I infect then?
You infected 9 people.
So from that 9, more got infected, more got infected.
Mm-hmm.
Wow.
With no immunity to our virus, by day 3, the infection has spread out of control through our volunteers.
Loads of people have this. All over the map. Oh my goodness. What have we done? Wow, it's everywhere. It's not even, you don't even just have little clusters anymore. It's literally everywhere. And people still getting infected. Oh my goodness. That is an extraordinary number of people to be infected from just one person walking down the high street.
Yeah.
In just 3 days, 86% of all people who took part were infected. Our pandemic virus spread like wildfire because no one was immune. If this had been a real virus, the town would have come to a standstill. Instead, it's created an extraordinary simulation of how an infection would spread from person to person. Even better, our app also reveals information that will help test how we can stop an infection spreading.
For those of you who were infected, your apps should also tell you how many people you went on to infect. How many people infected no one else? How many people infected 1 or more? 2 or more? 3 or more? 4 or more? 5 or more? How many did you get, sir? 6, and madam? 5. Okay, these are our super spreaders then. You got 6 people.
I got 6 people. I'm feeling very guilty about it. And I already know I need to apologise to a lot of people at the coffee shop.
Oh, is that where you think it was? Where you think it happened?
Friday morning.
You were sitting in the coffee shop?
I was.
But actually, I've just noticed, I spoke to you on my patient zero walk. You were in the hardware shop.
That's right.
Is that where you work?
I do.
Did I infect you?
I assume so.
Now, how many people did you then go on to infect?
8.
8 people? That makes you the champion. I mean, it's not a great championship to win.
No.
So, do you think it was just people that you were speaking to in the shop?
I think it's just a high volume of customers that we have, really. Popular shop. I'm quite impressed, actually. I don't really know. It's quite shocking, really. 8.
As our data reveals, when it comes to infectious diseases, clearly we aren't all equal. Pandemic researchers call people like Justine social super spreaders, and they're thought to be key players in the spread of a real infection. It may seem obvious that someone whose job or lifestyle brings them into contact with a lot of people could spread more disease. But this is the first time they've actually been identified like this. Thanks to the app, we can now test a potentially life-saving idea.
If we can understand who the super spreaders are, then it might help with control. For example, a situation where we've got a vaccine, but either it's in short supply or we've got a very limited time to deploy it, so we can't just vaccinate everyone. And you've got to make some choice about who you're going to vaccinate.
Be selective.
Exactly. And rather than choosing at random, you can be really strategic and choose those who are going to infect a lot of other people or would have infected other people. So on the left is going to be our original Hazelmere epidemic, And on the right is going to be our simulation of what would have happened if we vaccinate the super spreaders.
So how do you define that?
Yeah, so for this one, we chose the people who actually infected more than 3 other people, 3 or more.
So if you take those out,
yeah,
vaccinate them so they're immune from the virus,
yep,
and see how it changes.
Yes.
Okay.
And that was only 46 people, so it's a pretty small vaccine rollout. And what you see is the dots are in the same place, but...
So this is me, my little walk on the first day. A few, in fact, it's quite a lot going on this one. This is the one we've seen before. Much less, actually.
And we're in day 2 now.
Far less. Oh my gosh. Oh my gosh. So just vaccinating 10% of the population.
It's a much slower epidemic. We vaccinated 46. Stephen, you ran this one. How many fewer people were there infected than the super spreaders?
There were, 112 fewer.
Okay. 112. So that's people who weren't vaccinated but ended up not getting infected just by virtue of the fact that the super spreaders were protected away from the virus.
That's exactly right.
Gosh, it does make quite a big difference then.
We simulated the vaccination of only 10% of our app users, but targeting these super spreaders reduced the number of infections by 40%. Our app allowed us to identify super spreaders in Hazelmere. But in the real world, people who work in busy places like schools could also be super spreaders. Deciding who to vaccinate first with greatest effect is problematic. But there could be a way of identifying individual super spreaders before a contagion, and that could mean a revolution in pandemic prevention.
That's the theory being tested in a unique experiment. Researchers at Imperial College want to know if some people are biological super spreaders. Is there something about their genes that makes them become highly infectious? If there is a biological reason, there could be a test to identify super spreaders before an outbreak hits. And that's the revolution in pandemic control that could be starting here today.
It's about 7 a.m. and this looks like any ordinary hospital wing. In fact, it's a research facility. The patients through there are perfectly healthy for the time being.
Technically, Joydeep Dutta isn't a patient. He's one of 10 healthy volunteers being quarantined in this ward, about to be infected with a large dose of purified swine flu, because researchers are hoping they can pinpoint what makes people react differently to the same virus. Dr. Chris Chu is running the experiment.
There's so much that we don't know about flu infection, why some people get more sick than others, and in fact, we don't really know what contagiousness is.
To find out what might make someone particularly contagious, the team will dose Joydeep and the other volunteers with flu, then compare how they respond. Each of these vials is packed with 5 million swine flu virus particles, the same strain that caused the 2009 pandemic. Meanwhile, Joydeep is calmly waiting next door.
What made you want to do this?
I mean, I had a family member who had the swine flu in 2009, and it kind of, she was quite affected by it, and it changed her life to a certain extent.
What happens next is down to a battle between the 5 million virus particles and Joydeep's personal biology. At the moment, there's no way of predicting how he will react. Over the following days, his samples, along with those from the other volunteers, are tested to see how infected they've become. Everyone was inoculated with the same dose, which makes the difference in their results astonishing. Chris first shows me a sample from one of the other volunteers.
What you can see here is that every spot that's green is a cell that's infected with flu.
So you're physically seeing swine flu virus right there, and it's showing up green.
Exactly. So
But Joydeep's samples look radically different.
Joydeep has made a lot more virus in his nose than the other person. You can zoom in on one of those areas where it's particularly dense, and here there's one which looks like it's swollen up and falling apart.
Oh, wow. It literally does look like a sort of, almost a puff of smoke. So that's a cell that's bursting open in death, so to speak, overwhelmed by virus.
That's right, yeah. That's exactly what's happening.
It's a very early result, but it suggests that there is something specific about Joydeep's biology that could make him particularly infectious.
Do you think you actually might be able to find a genetic test to predetermine who might become really contagious with flu?
Yeah, so that would be the ultimate hope.
Wow.
Viruses travel wherever we take them, from town to town, or village, or city. Which is why 3 weeks ago we also launched our national experiment in the hope of getting 10,000 people to take part.
The second phase of our experiment is going to use the BBC Pandemic app to collect data from volunteers all around the country. And our mathematicians are going to calculate how quickly a Spanish flu-like virus might spread. We'll find out how many of us could get infected and how many of us could die.
In the national experiment, users will catch our harmless virtual virus as soon as they start the app. This time, they will be tracked once an hour for 24 hours. The aim now is to track journeys around the entire country, across cities, and between towns and countryside. The app also asks users for their age and gender, and to report the age and number of people they encounter during that 24 hours. The aim is to collect data that will improve our understanding of how much we actually move and mix. For example, do some age groups travel more than others? How isolated are older people? If we can recruit 10,000 users, it will be the largest, most detailed UK dataset ever collected. How far and how fast a lethal pandemic could spread across the country.
If a virus that was carrying a very high case fatality became transmissible through the air between people, we could have a devastating pandemic on our hands. Millions of people could die around the world.
We know that a pandemic will come. There's no doubt about that. These are regular occurrences. What we saw from the last flu pandemic in 2009, which was a relatively mild disease, was that our health service was almost unable to cope.
Social media and maths are unlikely weapons, but they are essential in the fight against a pandemic. Despite all the wonders of modern medicine, another Spanish flu-like virus could still bring society to a halt.
You may have thought that the huge number of fatalities seen during the Spanish flu pandemic is something that we could relegate to a bygone era, and that's partially true with modern medicines such as antibiotics. Antibiotics would be useful for the secondary bacterial infections that flu victims often suffer and that often kill them, ones like bacterial pneumonia. But antibiotics would not be the cure-all because they do not work against viruses.
Antibiotics treat bacterial infections by interfering with the processes that keep bacteria alive. But viruses aren't alive. They're just bags containing genetic material. Which means antibiotics are powerless against viruses. What you need are vaccines. Every autumn, thousands of us line up to get a seasonal flu jab that's tailor-made each year. The vaccine is designed to produce antibodies that block the spikes of the specific flu viruses circulating that winter. But the problem with a pandemic flu virus is you only know about it when it started making people ill. And designing a vaccine takes time. I need to find out how much time, so we can factor that into our predictions about the spread of the BBC pandemic. So I've come to one of only 2 factories in the UK that produce flu vaccine. At the moment, it's busy pumping out millions of doses of seasonal flu vaccine needed each year.
So this, I'm going to take you down this area here.
All of them rely on these.
This is where the eggs come in from the farms.
Dr. Laura O'Brien is in charge of this site.
This afternoon. That's absolutely fascinating.
Laura, why are we using eggs to make vaccines?
So we've used eggs for decades to manufacture influenza vaccine, and viruses need living cells to grow. And if you think about a single egg, there's lots of living cells in there. It's protected by its shell, so it's almost a clean environment, and it's just the perfect place for virus to propagate and grow.
I mean, there are a huge number of eggs here. How many do you handle in a day?
Every single day, you know, Monday through to Sunday, here in the plant, we're putting over 500,000 eggs through the factory. So the eggs have been incubated.
Right now, this factory is making only seasonal flu vaccine. Each fertilized egg is inoculated with flu virus, which then replicate. After just a few days, the eggs are packed with the virus particles. Then all those virus particles are inactivated to make the vaccine, so they're powerless to cause flu, but can still fool the human body into making antibodies.
We put them in different incubators, so not all the one day's batch goes the same incubator.
When it comes to making flu vaccine, you first need to know which strain of the flu virus to grow inside the eggs. A global monitoring system run by the World Health Organization constantly watches out for animal flu viruses that have hopped into humans. It's the WHO that declares if one of these pandemic viruses is on the loose. Laura, presumably when a pandemic is declared, production changes.
When the strain's declared, that's the big bang, when the pandemic's declared. Here at the site, we have a pandemic response plan that we immediately enact.
It's a race against time to isolate and identify the pandemic virus so that a vaccine can be created and put into production. It really is all hands on deck then, there's urgency. How long can you expect, sort of, from that get-go moment to produce your first batch of vaccines?
What we see is for a pandemic strain, generally in industry, it takes about 4 months from that strain to actually getting those first doses out there to patients worldwide.
At least 4 months before a pandemic vaccine is tested and available. That's a sobering thought. So just how many of us could become infected before a vaccine is available? We can use the results of our national experiment to find out. We launched the nationwide BBC Pandemic app a little over 2 months ago. We needed thousands of people of different ages in different locations to catch our virus, to get real detail on how people move around the country and who they come into contact with. So how did we do?
Adam, when we met a couple of months ago, you set me a challenge to go out and get a data set for you. Just remind us of what it was you were looking for.
The aim was to get data on social interactions and movements. We know these kind of things are important for diseases, but really to have those things combined and have a large number of participants would be really valuable for predicting epidemics.
And Julia, you've got the results, I know, of how many we actually managed, because we needed 10,000, right? That was the number that you said.
Are you ready?
Yeah.
Oh, that's brilliant. So almost 29,000.
Well, that is impressive. And that's proper, full, rich, glorious data for every single one of those people.
These are all users who've used the app, and we've got information on movements, locations, the contact survey, all the bits of it together.
But before we predict the spread of a deadly virus through the UK, we still need one more piece of information for the model. How easily the flu virus can spread.
One of the ways we can tailor models to a specific infection is to use a value known as R0. And this measures, for a specific infectious person, on average, how many infections they generate.
So how many people one person goes on to infect?
Exactly. If you drop one person in a susceptible population, how many new infections will they create?
And that's definitely different for lots of different diseases, isn't it? So, you know, measles, Ebola, ones I've got in my head. But
exactly. So for Ebola in West Africa in the early stages, it was around 2 in some areas. So each case on average was generating 2 additional cases. But for measles, it's much higher. It can be 15 or 20 in some.
So one person can infect 20 people before?
If it hits a susceptible population, exactly, yeah.
That's why vaccination is important in that one. So what number did you actually use for flu?
We looked at past pandemics. A typical range is 1.5 to 2. And what we've done for the BBC pandemic is we've got an R0 of 1.8.
Okay, and that's not massively high.
That's not crazy high for a pandemic. It's a reasonable scenario to be planning for.
This is what we've been waiting for. Thanks to nearly 30,000 app users, we've now got the best data ever available for our team to use in their calculations. How many people in the UK does the mathematical model predict could become infected if a Spanish flu-like pandemic began in Hazelmere today?
So Hazelmere is glowing in red here, just so we can see where it is, as well as seeing the spread, which will be the dots going towards red as the cases increase. We'll also see a bar with the total number of infections. Ready?
So it hits London very quickly then.
And then we need to zoom out.
We're already zooming out. Look at it, it's literally sweeping through.
We had the Glasgow and Belfast area go off before Edinburgh.
Oh, 43 million people.
And that number is extraordinary.
43.3 million, which is about just over 2/3 of the country.
Based on data from thousands of app users, the model predicts very few parts of the country will escape infection. Only the most remote corners remain blue. But the prediction of the number of deaths is even more shocking. By the end of May 1919, the death toll from Spanish flu had risen to over 150,000 in England and Wales alone. Globally, it's thought at least 2% of people affected died. Based on the worst-case scenario of 43 million infected nationwide and then falling sick, a 2% death rate today would be utterly catastrophic.
My word. That's an enormous number.
It is an enormous number. So that, in the worst case, that's the number of deaths that we could expect based on our data in a future pandemic.
Over 800,000 dead, millions more infected. And there's one more piece of shocking information that our calculations can reveal: how quickly those deaths will happen.
Over what period are all these deaths going to be seen?
Yeah, so we can have a look at the timescale, and I can show you that here. What we're going to do is go through, and we're going to see with the time up there. So you've got the day up there. So we're back to day 1, back to Hazelmere. So this is 1 month in London. 2 months in, you can see it's made it up to Glasgow, Edinburgh, Belfast.
You can kind of see it moving.
There's a few long-distance stumbles as well, right?
Yeah. Jumps over to Northern Ireland.
Yeah, I mean, that was just by about day 60, 2 months, wasn't it? Even well before it got to Aberdeen there.
You don't have very long, do you?
No, that's really frightening. But presumably, I mean, this is, you know, you've got a timescale there, but presumably pandemic flu isn't going to arise for the first time on this planet. It's not likely to be Hazelmere. It'll be across the globe somewhere.
Yeah, chances are it'll start somewhere else in the world. Based on what we know about these kind of viruses, it may well be somewhere in rural Southeast Asia, for example.
And what sort of lead time might we have on that sort of knowledge coming to us?
Potentially if it emerges there, we'd get, say, 2 to 4 weeks before it actually arrived in the UK.
Okay, let's call that a month. And then we've just seen it takes just about 2 months to get from right near the south coast all the way up to Aberdeen and Belfast. That's 3 months, and I learned that you know, it takes at least 4 months to get pandemic flu vaccine out. So there's a real gap there.
Our data reveals an alarming reality. We forecast over 800,000 of us could die if a pandemic spreads unchecked throughout the UK. 43 million could become infected before a vaccine is available.
While researchers will be given all our data to help plan for the next contagion, another solution to the pandemic threat is being worked on in labs around the world. One of those labs is at University College London. It's run by biochemical engineer Dr. Tarit Mukhopadhyay. Researchers like Tarit are working on radically new ways for making enormous quantities of flu vaccine quickly. Instead of eggs, Tarit is growing vaccine in yeast cells in a steel vat called a bioreactor. The bigger the vat, the more quickly mass doses of vaccine can be produced. But there's an even bigger revolution in the offing.
Well, the holy grail is actually try and create a universal flu vaccine, right? And so this is a vaccine you don't need to constantly update every year or indeed wait for a pandemic to emerge before you can create a vaccine.
The coats of flu viruses constantly change, meaning a new vaccine is needed for each one. But we now know some bits of the flu virus don't change so easily. Make a vaccine that targets those stable bits of the virus, and you've got some protection ready and waiting when a pandemic virus emerges.
Rather than constantly having to update the vaccine, a vaccine that is based upon the universal system may be good enough for 5 years, and I guess the holy grail is making a vaccine that's good enough for 10 years. I mean, we will have to update it at some stage, but it gives us a little more breathing space and a little more flexibility in trying to deal with future pandemics.
That really does sound incredible to achieve, but how close are we to doing that?
Well, I guess in terms of getting a universal vaccine out there, I mean, we're still at least 1 decade, if not more years away than that. I think getting a commercial universal flu vaccine out there is still a long way away.
Until we get there, our data will put pandemic researchers in the best position possible. As well as their long-term forecasts, good GPS and contact data will be essential for them to model accurately during a pandemic.
I think this would be incredibly useful, just having this scale of data, but also having it by a different age group, by different geographical locations. It means we can really look at things in much more detail than would have been possible before. To have this kind of data for 20,000 people, that's just incredible. We dream of that kind of data.
You're welcome. It began by recruiting a community. It's turned into the biggest citizen science experiment in pandemic research. It's brought some harsh realities into sharp focus.
My word.
That's the number of deaths that we could expect based on our data in a future pandemic.
But our pandemic experiment has created an invaluable legacy to help us prepare. Because when it comes to a flu pandemic, it's not a matter of if, but when.